Okay, let's continue with our crystal field theory. Okay, octahedral fields. So we kind of talked about what this looks like. So your octahedral field is the exact geometry you would expect. Let's get plus. Okay, so you have your central metal. You have these ligands. Let's see. Think of these like X, Y, and Z axes.
Sure.
Should have made that more equal in length, but so we're just treating ligands as point charges interacting with the metal in the center. Okay. Okay, so we need to start talking about how this actually splits. Okay. So some of these d orbitals are going to stabilize and some of them are going to go way up in energy. Okay. And so you're used to d orbitals that look like this, 5 degenerate d orbitals.
Sure.
Okay, but let's okay, so if this is my X and Z and Y, let's just, for example, think about your dx squared minus y squared. Okay. So that means you're going to have go there, on there. Okay, so and you get that those alternating phases as you go around. So let's look at what happens. Do you notice how, let's see, that point charge, that one, and that one, will end up striking this orbital head on.
Yeah.
That causes a destabilization. The more, and now I want you to think of this in terms of more or less electron interaction, because the octahedral is fortunate, it's good to start with because you get actual head-on collisions. Now, when we get to tetrahedral, you're going to see that you don't necessarily always get head-on collisions with the d orbitals, but you get more interaction versus less interaction.
Okay.
This time, your head-on collision is your maximum interaction. That's going to destabilize the dx squared minus y squared and send it way up in energy. Okay? The same thing's going to happen. Oh, let's see here. What if I do that? Kind of hard to see, but it's on the next slides. Your dz squared orbital. Again, you're getting a head-on interaction, and you're getting still a little bit of interaction around that radial area due to that the donut. That's going to destabilize dz squared and send it way up. Now, if you go ahead and you draw like your dxy, your dyz, your dxz, you'll notice that these ligands have less interaction because the ligands don't strike those orbitals head on. Those orbitals are going to become stabilized and they're going to drop in energy.
Because those ones will be like halfway in between the. Okay.
And so what you're going to get is your octahedral split. Okay. So you can kind of start by looking at this. You have your cation, and you see that first image there where you have a spherical symmetry. In a spherical symmetry, like let's say you just have like an electric field that's spherically symmetric, all of your d orbitals will stay symmetric, but then that breaks apart into 4 individual point charges that smack the metal ion, and you get this split. What you see there now is you see the delta is not 0, it's delta O. So this is your energy separation for your octahedral complex.
Okay.
Okay, so in these energy separations, you'll see delta O, delta tet for tetrahedral, so on and so forth. But this splitting is one of the things that's going to determine what we will come to see as low spin versus high spin. So this is where, okay, you need to start kind of thinking about, and this will take practice. You need to start thinking about this in terms of the off-ball principle competing with Hund's rule. So the off-ball, do you remember what the off-ball principle says?
Okay. Hund's rule is that it's gonna fill in like all one spin and then a little pair.
Yeah. So Hund's rule wants to do that before any pairing occurs. What's off-ball principle?
Off-ball is it'll go bottom or lower energy and fill up.
You're going to start getting a competition between these two.
Okay.
So for example, if that delta O is massive, if it's too large, then you're going to get the off-ball principle because it'll take too much energy to put the electron into the next level. Okay. And you're going to come to know this by comparing your energy separation versus pairing energy. So how much energy does it take to pair electrons versus how much energy does it take to place electrons all in parallel spins? Now, so of course, here is your dz and your dx squared minus y squared. So of course, you can see those ligands coming in and interacting and causing that split. Now, every single field is going to have its own unique split. Some people memorize them, some people learn to predict them. I suggest at this level doing kind of a combination of both. Because eventually, like let's say you use this in laboratory work, you're going to use these enough that you're just going to kind of eventually know what they are. I think of some biology thing now that you just know like that, but you didn't a couple of years ago because you've used it enough. Well, this will become one of those. Okay, so sometimes you'll see this too. This is a mathematical concept. This line here is known as the centroid. So that's just the center of your symmetry. And then energetically, how far are these orbitals away? How far do they move from that centroid? And we're going to be able to judge that because you can see, for example, we have more energy separation going up than we do going down.
Okay. So centroid literally the same energy as the like ball sphere that you
Yeah, so a centroid is a it's a very exact mathematical representation, but it's the geometric center. So we use it a lot in gravitational physics, where your center of gravity is known as the centroid.
Okay.
So it's just, but there are very specific ways to calculate it, and it gives you a more exact answer. Okay, so here, I should have wrote that better. So of course this is our OH character table. Now what's going to happen is you notice these three at the bottom, dxy, dxe, dyz, and then the two at the top. You notice how the three on the bottom are degenerate, the two on the top are degenerate. So that tells you that as far as the symmetry of these orbitals, first off, the one up here has to be E. Down here has to be T. So the E is the doubly degenerate, the T is the triply degenerate. Okay, so we know that. It's just which ones? Well, the E is simple because I have EG or EU.
Right.
So you're looking at a center of inversion. Are those symmetric or anti-symmetric with respect to inversion?
Symmetric.
So that's EG. So that's your EG. That's your EG level. So you're going to see representations of this, and that top level will be marked as TG. Down at the bottom, well, you're going to get a G because those are symmetric with respect to inversion.
Right.
And then, what if I put a C2 axis there?
It's not symmetric.
Not symmetric. So is that a 1 or a 2?
2.
2. That's a T2G.
T2.
So that's your T2G level. Am I supposed to do that right here? Okay, so what we're going to start to get is let's go ahead and draw this separation. I'm going to draw my 5 there. Now we enter an octahedral field. We get my T2G level. This is my dxy, dxz, dyz. Okay. T2G level. And then of course up here, dz squared, d minus squared minus y squared, and this will be my EG level. And then my centroid is going to go right through here. All right. Now what you're going to start to notice is if we look at these, that'd be a good color. So you're going to put a line here, and then one up at the EG level, then one down at the T2G level. And what you're going to notice is this one is going to be a 0.6 delta O, that full separation energy, which we can mark as that full separation is your energy. And then down here, now it depends on the source you use. So since we've relaxed, we've stabilized from the centroid location, these orbitals are now lower in energy. So some sources will write this as a negative 0.4 delta zero. But so in this case, if you did the difference between those two, you get 0.6 minus 0.4, and you get a total of 1 delta zero. So those two, and some people will write that as a positive 0.04 and just add them. But overall, you get that full delta zero separation. It's just you get a fractional split of the energies going up or going down. Now, we can actually figure this out mathematically. It's simpler than you think. So we can say that two orbitals some energy x up, and three orbitals go some energy y down. And so, and the centroid is your zero line. So we can say, well, if I have my 2x plus my 3y, that's going to have to get me back to the centroid. Okay. I also know that x minus y equals my delta O. Okay, well, so if I did x up, that's going to be my EG. My y will be for my T2G. So let's look at that. So let's solve for the EG. So I need y is going to be x minus delta O. I can plug that in here. And 3/5 is your 0.6. But it helps to be able to see this because some textbooks just leave it as 3/5. You can do the same thing. And when you solve for it, your y will come out to your 0.4 delta 0, but it just depends on the source or how you feel comfortable writing it. Do you call it negative 0.4 because it's below the centroid 0 point, or you just keep it as the 0.4? It really is going to depend on how you're comfortable. You just need to know that that split from the centroid is 0.6 up and 0.4 down.
Yeah.
Okay. Sometimes you also see textbooks write this in terms of what they call differential of quanta. So you can translate that because one is 10 differential of quanta. So you can always translate that. Yeah, so some textbooks will have DQ there, and you're like, what the hell is DQ? Well, it's just a mathematical translation from one to the other. Okay. We need to start talking about weak field versus strong field ligands. Okay. The magnitude of your delta O is determined by the strength of your crystal field. Your delta O for weak field ligands is smaller than your delta O for your strong field ligands. This is also going to start to determine your low spin versus high spin. You can really judge by looking at the spectrochemical series here. Oh, there's water on here.
There it is. Between the.
Oh yeah. Okay. So water is kind of a splitting point. It's usually sometimes it's considered strong, but it's kind of considered a middle strength ligand. And some of these you'll have to look up until you get used to them. But just know that area there with water is going to be kind of a central strength ligand. Ammonia is also kind of a central strength ligand. So you kind of get an idea of what you're looking at. And anything to the right will be a strong field. Anything to the left will be a weak field. But you can also look. Your weak field ligands are specifically pi donors. So halogens, highly electronegative, but they hold large, but they're large and hold their valence electrons rather loosely. So if you think of your coordinate bonds, your halogens are going to be the electron donors.
Mm-hmm.
Strong field ligands are pi acceptors. Now this is a little more roundabout because we know that the ligand is initially going to donate sigma electrons. Like take your cyanide ion. Initially, it's going to donate sigma electrons, but then it's going to do something called pi back bonding. And your pi back bonding electrons will then be back donated from the metal into the pi structure of the cyanide ion. It creates a stronger bond. And it donates specifically into the pi star level of cyanide, which is your cyanide there is like a triple bond, which is going to break that triple bond into a partial bond, but then the rest of that bonding energy will go between the metal and the cyanide. So it's going to then create a partial pi bond with the metal.
Okay, but it's like it's kind of shared between the nitrogen and the carbon and the nitrogen.
Well, okay, so let's think of it like this. So your metal Oh, even if I get this wrong. So something like this, okay? Initially, the ligand is going to share sigma electrons.
Okay.
Okay. But then, because of the nature of carbon and the structure of this molecule, what's going to happen is the metal will then backshare electrons into the pi star level.
Mhm.
Okay. So now you have your metal sigma bond. And you notice how that backsharing into the pi star level has decreased the bond level, decreased the bond order between carbon and nitrogen.
Sure.
And then what you're going to get is partial pi bonds. And so this is called pi back bonding.
Cool.
And it really increases the strength of that bond. And so this is a strong field ligand, and this is going to cause that delta O to greatly increase, leading to what we know, what you'll see is called as low spin.
Cool.
It's a concept you have to work with, but you get used to it eventually. I wonder if that's the same. One of the ligands I would actually look up and learn, especially if you're, there's several on here I would look up and learn, being a bio person as well, because they're so common. Of course, pyridine.
Yeah, pyridine.
The EN, the BIPI, that is so common. But some people also call it BPY.
Is that bipyridine or something?
Yes. Your phenol, and I forget the name of it now, but the PPH, I mean, that's more inorganic, but you see it quite a bit. I would know what those abbreviations mean. Once you look them up, you're going to go, oh, I know what that is.
Yeah. I know we've definitely used quite a few of them in OChem,
Mhm.
at least.
Yeah, so I would just make sure I know, like I know my abbreviations. This one is not an abbreviation. I don't know if you caught that. That's the thiocyanate ion, and it's thio because it has what in it?
Sulfur.
Sulfur. Okay, so we can actually get an estimate of that energy separation, delta O, by using electron absorption spectroscopy. Another little laboratory tool for you to use. This one's very, very popular in experimental procedures, so I would learn about it because you will probably be using it someday. It's called UV-Vis.
Oh, UV-Vis.
Mhm.
I've heard of it.
So yeah, you're bombarding your molecules with UV invisible photons, and you're looking for these absorption bands. And the absorption bands represent, so like you have an octahedral complex. These absorption bands are going to represent the transition from the electron excitation from a T2G to an EG orbital.
Oh, okay.
So now that separation, even though they're all d orbitals for the metal, is now considered an excitation.
Mhm.
So you can start to see this very different behavior from metals.
Mhm.
And you can evaluate it by you look for your lowest what? Well, your lowest energy absorption, that's going to be your lambda max. And then you place it into here, you're using your basic Planck equation, your HC over lambda max. And that gives you a pretty accurate estimate of that delta O. H, of course, is your Planck constant, C is the speed of light, and you have to find the lambda from the UV-Vis spectrum.
Okay.
This would be a good one to just read about, because like I said, especially in like biology and chemistry research, especially if you're going to be like strong experimental, you'll use this.
Right.
Like I would also very strongly suggest you get your NMR down.
Yeah, NMR.
You're going to use that a lot. I'm trying to think of the stuff that I know for biochemical, bio or research, but I know NMR, UV-Vis are going to be big. Various types of spectroscopy will be big, but definitely your NMR, your UV-Vis. You just make sure you have an understanding of these processes so that when you walk into a graduate lab, you're ready to go running your first molecules and you have an idea of what you're looking for. Your PI will be super happy if you already have an idea of what it is.
Nice.
And you go, oh, look, there's the lambda max absorption. If you did that like your first year, your PI would go, I'm putting you on so many projects.
Yes. That's funny.
It'd be like, oh my God, there's so little I have to teach her comparatively.
Yay.
Let's see, where are we? Okay, so and when we're talking about lambda max, let's kind of look at how some of these are how some of these are judged. And also like looking at some trends. So we can start with say, let's look at this octahedral complex. Okay, well, what is the charge on the chromium?
It's gotta be okay. Wait. 3+.
3+. That's chromium 3. When we look at the periodic table, we see that the chromium 3 is going to have an electron configuration, which makes this a D3 complex. Okay. Now, when you're looking at UV vis data, I want you to tell me what this is. Your delta 0 going to be is compared to
Gosh.
you've seen that before. I know you have.
I know.
And your brain's going, crap, I know this.
It's
What do we call those?
what do I call those?
Yeah, 1,500 inverse centimeters.
The
15,000.
the wavelength.
Close.
It's a frequency.
Closer.
Closer. Gosh.
It uses the Greek letter nu, which we use for frequency, but this one has a bar over the top of it.
Yeah. Okay.
What if I told you that it's pretty well equal to 1 over lambda?
Yeah.
I can tell by the way you're acting. You're like, I've freaking seen this.
We talked about this in physics, right?
These are called wave numbers.
Wave numbers.
Mhm.
Yeah, we just did.
Yeah.
Okay, that's fine.
So
That's fine.
no, that's the thing. Like I could tell from your reaction, like, oh crap, I've seen this.
Yes. Yeah.
Okay, so your UV vis data is going to come back in wave numbers.
Okay.
So you can start to then break that down and compare that and go through your simple calculations and get an estimate of your delta 0. That's why your delta zeros are like you'll see in papers, you'll see delta 0 as 15,000 wave numbers. You're like, well, that's not an energy. Well, but when you get to that point, most chemists are going to read energies in terms of wave numbers.
Yeah.
It's because that's what you get back from the experiment. That's the experimental data. And so they're like, well, I mean, it's going to look 1 over lambda. Your energy is proportional to 1 over lambda, so it's just some constant times that.
Sure.
You know, so that already. So if that gets bigger or smaller, the energy is getting bigger or smaller proportionally. It's in the same way. So yeah, a lot of your articles are just going to be in terms of wave numbers, and as a good chemist, you'll start going energies.
Okay. Yeah. Not knowing that put like a twitch in my eyebrow for a second. Like that stressed me out.
But the good thing is you've seen it, and your brain is going, it's in there.
It's in there.
Whereas for so many other students, I just get a blank stare, like I don't care, just tell me. I was also thinking, for your hair, you either need to do like a Sabine Wren.
You said that.
Or do like an X-Men Storm.
Oh, that's true. That's a good point. Yeah. Last time I bleached my hair, it was still green. I don't think I can get the grain out. I think it's in there until I have no hair.
Well, then if you did the Sabine Wren, you could start with the white. Just good.
Yeah, well, I just don't think I can get it. It's just gonna be green. Like if I bleach it, it'll still just be a lighter green.
Really?
Yeah.
Oh, that's strong green.
I know. I'm doomed forever.
All right. So this one here, this is a weak filled ligand, so your fluoride. So, oh, where did I put it? Okay, your weak field ligands tend to lead to high spin. Okay, so this would be a high spin D3. Now, as a high spin D3, where are all of your what level are all of your electrons going to be? Let's go back up and look here.
Oh, they'll all be in the T2G.
Yeah, T2G. Because, I mean, if you went high spin D5, you're going to fill all of them with one electron, but you're still going to go lowest energy to highest energy.
Sure.
So a D3 is going to fill the DXY, DXC, DYC first. Now let's go with kind of some midfield ligands and then a strong field ligand. See, there's the chromium 3 coming out. So you know this is still a D3 complex. And the UV vis data. Okay, my other midfield ligand. And midfield ligand is not actually a term. It's one of those things that doesn't exist, but every chemist will go, yeah, it's there. You know.
Yeah. Loosely defined.
Yeah. Okay, so I went from a weak field ligand to midfield ligand, so I'm going towards stronger. Okay, and you notice that the energy, let's see.
So this is lower energy.
Yes, so the energy is going down.
Energy going
down. Let's see. Let's take a look. No, energy's going up. Okay, so your weak field ligands. Okay, so here's the way you look at it. Your weak field ligands providing more high spin states or providing high spin states. High spin states occur when that delta O is minimized. When the energy gap between the two is lower, so if your P is your pairing energy, you're going to get that high spin. If it costs more energy to pair than it does to put electrons in the EG level, then you're going to have a high spin.
Okay.
And then so you see that your weak field produces the lowest energy, so you would expect a high spin. Now you're starting to go up. You're kind of at this realm, like your water is still technically going to be a high spin. Ammonia can go back and forth based off something we'll talk about in a minute. But you notice the energy is going higher. And these are both considered kind of midfield. But if you look, water is a weaker field ligand than your ammonia. Okay, so you follow this spectrochemical series and you say, okay, well then that makes sense. The ammonia is going to produce the higher energy.
Okay.
What do you think is going to happen with this ligand? So this is still your chromium 3 D3 complex. Higher or lower energy?
I think that was going to be higher, right?
Yep. Because now we are in a definite strong field ligand. So yep, we get the highest energy of this grouping. So you can see when you have a metal center, when you have a common metal center with a common oxidation state, the strong to weak field ligands are going to dictate the energy of the system. And as we said, your weak field ligands lead to high spin states due to smaller delta O, while strong field ligands lead to low spin states due to the larger delta O. And again, you're just looking at that gap between the T2G and the EG going, how much energy would it take to low spin versus pair electrons in the or high spin versus pairing electrons in the low spin?
Sure. What exactly do you mean, like high spin, low spin? Is there a good definition for that?
Yes, and we will get there.
Okay.
We will, yeah, you'll see the difference.
Okay, cool.
Okay, the best way to think about it is think of all of the arrows you can put in there as angular momentum, +1/2, -1/2.
Sure.
High spin would be maximizing that. So imagine I had 4 electrons, okay? And I put them like this, okay? 1/2, 1/2, 1/2, 1/2. That's going to give me 4 halves, or a spin of 2, an angular momentum of 2 versus that's going to give me 0. So the left is high spin, the right is low spin.
Okay. Word. That actually really clears it up.
You're also going to learn terms like this over here, the one on the right, all of that spin of 0, that's called a singlet.
Mm.
And then you see your 4 unpaired parallel electrons. That's called a quintet.
Oh, okay. So just like the number of groupings that you have?
Well, you're really looking for the number of your. It can get more confusing when you have unpaired electrons with an anti-parallel spin. But for right now, we're keeping it simple because you're not doing graduate level quantum chemistry. Maybe someday, I'll hold out hope.
Okay.
But you really want to count the number, and let's just imagine that there are no unpaired anti-parallel electrons. You want to count your unpaired electrons with parallel spin, and then add 1 to it. So you see 4 unpaired electrons that are parallel. That's 4. You add 1 to it, you get a quintet. Okay. Because your 0 starts at a singlet, starts at 1.
Okay, and then you just n plus 1.
Mm-hmm.
It's like NMR peaks.
Yeah.
Okay.
So you'll also see this in literature and textbooks and stuff, and it's language to get used to. So if you see a sextet, you go, oh, well, that's 5. That's 5 unpaired electrons of parallel spin.
Mm-hmm. Okay.
You know, so it's just you trying to a big part of this class is also getting you used to the more advanced jargon, because I guarantee you when you're done here, if you pick up an article, you're going to read through and go, oh, I know what that term is now. Or this table of wave numbers, I know what these are telling me.
Heck yeah.
Okay, so apparently I thought I need more room, but okay, so now for complexes with the same ligand and the same metal, delta O increases with oxidation state of the metal. Okay, so let's take a look at this. What about this complex? What is the oxidation state of the iron?
The oxidation state of the iron.
Oh, hang on, it's not 3+, it's 3-. That would be a really high oxidation state. There we go.
It's going to be like 6-, right?
No.
No.
Well, which one?
For the iron.
Well, the iron, the metal has to be positive.
The metal has to be positive.
What is the charge on the cyanide ion?
It's -1.
-1. Okay.
So wait, this isn't the same as oxidation number.
Yeah, it is.
It is? Mm-hmm. So isn't it just like I've thought about this in an OChem way, so it might be a different way of looking at it. I was just thinking of like the electrons being pulled away from the.
Well, think of it like this. If I have 6 cyanide ions, that gives me a -6. Iron does something to get me to a -3. What is the charge on iron?
3.
Mm-hmm.
Okay.
And when you look up the spectrochemical, let's also talk about what kind of D complex this is. Iron 3, look at the periodic table, and you get that argon core. So of course, again, you're going to So iron, I'm going to give you, I'm going to give you neutral iron. Okay. So what is iron 3?
What is iron 3? You're going to be 4d3, right?
Well, which 2 electrons go? I have to take 3 electrons off.
You just take 3 electrons off.
Which one?
Oh.
Which 2 come first?
They're gonna hold on. I did this wrong. It'll come off with the 4s.
So that's 2 electrons. Then I need 1 more. Where will it come from?
Off of the 3d.
Yep. And so you're left with what?
It'll be argon and then 3d5.
Yep. So this is a D5 complex.
We got there.
Versus, let's take a look at this time the oxidation state of iron is what?
2.
2. So, I mean, simple enough. That means this is going to be a D6 complex. And then let's look here. The delta O for the first one, 35,000 wave numbers. Delta O for the D6 complex, 33,800 numbers. So you notice that the higher oxidation state, so the iron that's more positive, produces a delta O separation that's greater. So in complexes like that, now granted, that's a very strong field ligand, so you're predominantly going to get low spin. But you can also see a situation in which this oxidation state could make you bridge from low spin to high spin. Okay, well, we made up that minute, so.
Okay.
Okay, so we'll just keep working our way through this to get an idea of how these complexes build and how they work.
Cool.